In this video, we're going to talk about the Unit 1 review for the fall final exam. In Unit 1, all the way back in August, we talked about things like the history of the atom, subatomic particles, or the parts of the atom, and ways that we can apply the information we're given. The first major scientist to contribute to the atom that you need to know about is J.J. Thomson. He is the first scientist to discover a subatomic particle, or a particle that's smaller than the atom, and he named it the electron. He discovered it using an experiment called the cathode ray tube experiment, which is really similar to the Crookes tube experiment. We're going to take a gaseous chamber and connect it to a power source that emits a light that goes through a magnetic field. We can have a positively charged plate at the top and a negatively charged plate at the bottom. And when he turned on the device, he noticed that the beam of light was attracted to the positively charged plate, meaning that it must be negatively charged. Because he is the first to discover a subatomic particle, he believed that the electrons had to be with something to balance it out. And so he thought that the atom was mostly comprised of a positive jelly-like substance, with electrons randomly embedded inside of it. And so he named it the plum pudding model because it looks really similar to a very popular British dessert that's really similar to pound cake with fruit embedded. The next scientist to come along would be Ernest Rutherford, who was actually a student of J.J. Thomson and took Thomson's model into the gold foil experiment. He was actually trying to discover something else completely different, and he made some interesting observations. So he believed that Thomson's model was relatively large and full of subatomic particles. And so he predicted that the gold foil experiment would look like what we see in the bottom of our screen over here, that there is not really any way for an alpha particle to make it through the solid gold foil. But what he actually ended up seeing or observing was something quite different. So his alpha particles didn't bounce back. They actually went most of the way through. And every so often, he would have a random alpha particle scatter in a completely different direction. So he was able to change two big things about Thomson's model. First was the particle size. We now know that the atom is actually mostly empty space because the particles are very small. And the particles are also concentrated into the center of the atom, which he named the nucleus. So two big discoveries or contributions from Rutherford. One, he changed that the atom was actually empty space. And two, he changed that the positive jelly wasn't everywhere, it was actually in the middle, and he called it the nucleus, which means that he made a new model called the nuclear model. He still believed that the electrons were in the atom, but they were just surrounding the nucleus in some way, until Niels Bohr came on a couple of years later and gave us our first model that specifically talked about the electron. So he stated that the electrons were going to travel in fixed energy levels, aka orbits, around the nucleus, and that if an electron wanted to move between those orbits, it would need to absorb and release energy when jumping and falling. Now, his model was very short-lived. It only worked really for one element, which was hydrogen. And so there was a lot of limitations put on it. And that's why we have the latest model, the electron cloud model that we use today. So electrons aren't fixed on those orbits or those energy level pathways. Instead, they're moving around the atom outside of the nucleus at the speed of light. And they might have regions where you will be most likely to find them. And so those are called our S, P, D, and F orbitals that we learned about with electron configuration. Now, outside of atomic theory, there are a couple of applications that go with the atom, things like emission spectra and light emission. That's going to happen when our electrons are allowed to absorb and release energy and move throughout the energy levels. This is how we end up seeing very specific wavelengths of light that our eyeballs interpret as different colors of light, which is pretty cool. And an emission spectrum can create this unique signature, which makes it really easy to use for identification. Inside of the nucleus of the atom, we can use it for isotopes, determining the identity of the atom and the average atomic mass of the atom. So when we're talking about isotopes, we're talking about atoms of an element that all have the same number of protons, but they're going to have different numbers of neutrons, meaning that they're going to weigh differently from each other, creating this average atomic mass idea. So the number on the periodic table that is at the bottom of the box is called the average atomic mass, and it is most likely a decimal number that is calculated using all of the different isotopic masses and the percentages at which they occur in nature. We can use the average atomic mass calculation equation right here to determine that average atomic mass by plugging in the mass and the percent abundance for each isotope, adding them together, and then dividing by 100. Now, a really unique fact about the average atomic mass is that the average in your calculator will always be closest to the mass with the largest percent abundance. So sticking with the nucleus of the atom, we can again use it for determining some subatomic particle values, such as the proton can tell us the element on the periodic table. If we know the number of protons in the nucleus, then we know the atomic number, and we can match it to that box on the periodic table. If we need to calculate the number of neutrons that are also inside of the nucleus, then we can subtract that from we can take the mass number and subtract out the atomic number to make that happen. An example of that would be in chlorine-37. The 37 after chlorine and the hyphen tells us the mass number. And so we can find the atomic number using the periodic table. And to discover the number of neutrons, we can subtract those two numbers and determine that the value is 20. Now we're going to take a look at some of the practice problems that are embedded within this section. For the first three problems, we're going to be able to use these images of the different models of the atom. Number 1, how does the current model show improvement over the previous models of the atom? So the current model is also known as the electron cloud model. And it wants us to ask, what's the big improvement of the electron cloud model over the other models in the table? So letter A, the current model shows protons inside the nucleus. That's not true. The current model is not the one that shows that for the first time. That would actually be Rutherford's model. Part B, the current model shows electrons outside the nucleus. This is not the improvement that the current model makes. Even though it talks about electrons in a cloud, it doesn't necessarily show them outside of the nucleus for the first time. Again, that was Rutherford. The current model shows protons have a positive charge. Again, we're going to link that to Rutherford. He's the scientist that discovered the protons using the Goldfull experiment, and he determined that they were positively charged with the alpha particles being able to bounce off of them. So the correct answer to this question is D. The current model shows electrons in S, P, D, F energy levels, and those are the letters for the regions where you are most likely to find an electron in a cloud. Question 2. Which model recognizes the merit of an atom having a dense positive nucleus that is surrounded by mostly empty space? So there are two key phrases that stand out to me in this question: dense positive nucleus and mostly empty space. That's going to be linked with Rutherford. Question 3. Which model shows electrons circling the nucleus in orbits at different energy levels? That's a key phrase for me, but has limitations in the probable location of electrons. That's going to lead me to Bohr's model, C. In question 4, we are asked to determine which of the following statements is the best for comparing Thomson and Rutherford's model. Whenever I read that kind of question, it lets me know that there might not be an answer that I think is absolutely perfect, but it is the best one out of what I've been given. So letter A, Thomson identified the nucleus as the source of the atom's mass, and Rutherford later revised the model by proposing that electrons were embedded within the nucleus. So the first thing that I like about this answer is that it's in the right order. Thomson is first and Rutherford is second. But what I don't like about this question is what they have linked them to. Thomson did not identify the nucleus. That was Rutherford. And Rutherford did not propose anything about electrons being embedded within the nucleus. So that is completely wrong. Part B. Rutherford's model showed that atoms consist mostly of empty space with electrons orbiting a central nucleus, and Thomson later refined this by proving that protons and electrons are evenly dispersed throughout the atom. So I'm not a big fan of this because it puts it in the wrong order. Rutherford's model did not come first. That was Thomson's model. And so I'll get rid of answer choice B as well. Answer choice C says that Thomson proposed that atoms were solid positive spheres containing randomly moving electrons, whereas Rutherford demonstrated that the atom's mass and positive charge are concentrated in a tiny nucleus with electrons occupying the surrounding space. This answer option puts it in the correct order, Thomson first and Rutherford second, and it also gives us a pretty accurate description of those two models, but we'll check on letter D just to be sure. Letter D. Both Thomson and Rutherford agreed that electrons orbited the nucleus in fixed circular path. That is not true. The only thing that Thomson and Rutherford agreed on until Rutherford produced his model is that electrons were just somewhere inside of the atom. So answer choice C is the best option. It's not perfect by any means, but it's definitely the best out of what we were given. Question 5. Which atoms in the table below are the same element and with what reasoning? So the subatomic particles in an atom serve different purposes. The electron's purpose is to tell us things about reactivity and light. The neutron's purpose is for isotopes and mass numbers. And the proton's purpose is for element identification. And so inside of our data table, we have 3 columns of data: electrons, protons, and neutrons. For me to answer this question, I would need to focus on the number of protons. And atoms 1 and 2 have the same number of protons, which would make them the same element. Question 6. Based on the data table, what is the average atomic mass of element 6? So we were given a data table that shows us 3 isotopes, X28, 29, and 30. They all have their own mass number and percent abundance. So we can type this into a calculator or write this down into the equation and calculate the average atomic mass. We're going to take our mass number from row 1, 27.98. We're going to multiply it against 92.2 plus our second mass number of 28.98 times our second percent abundance, which is 4.67. And then we're going to add on, let me move this over, our last isotope's data, which is 29.97 times 3.10. Now we're going to add all of those values together using our calculator. So let me grab mine right quick. And you can type it exactly as you see it, parentheses and everything, just not the average part, obviously, because that's what we're calculating for. And you're going to get a value of 2,807.99996.